Yeah, thanks for coming in this morning. It's you all guys been having fun? Code 1, what do you think of the event so far? You're happy? Sorry, it's about to get a lot better? Oh, right, okay. Yeah, as soon as I leave the building, yes, yeah, definitely the quality is going to go skyrocketing, right? Right, so here to talk about Java memory leaks. So I'm just going to test arms. Everybody's arms working. Hands up. Who's had a memory leak? So I expect, yeah, right. Maybe the better question is, the passive question is, who hasn't experienced a memory leak at any point in time, right? If they haven't, they haven't. They probably don't know they haven't. Oh, right, exactly. And they haven't, yes. Yeah, sorry to inform you, you are suffering from a memory leak. Yeah, I have that all the time. So anyways, I just wanted to do this short, 45 minutes, so I'll go burning through stuff. It's a condensation of a 4-hour workshop that I do on the subject, so you can get an idea what's going on. Probably won't be as in-depth as the 4 hours, but hopefully we will get to, this button is kind of going weird. I was hitting it yesterday, and it was like always double forwarding. Oh, about me. So that's about me, slide stuff. Co-founded jClarity. And you might notice the Microsoft and Azure thing over there. That's because 19th of August, we were Borged. So now I'm actually principal engineer, part of the Java platform group within Microsoft. So we're planning on having fun digging around in the internals of the JVM to make life better for everybody, and particularly those people who are using the Azure cloud. And also, we'd like to talk about jCrete because, as we say, it's the hottest unconference on the planet, right? And we have in July. Right, so memory leak, chronic condition which an application retains a growing amount of memory that is never accessed and is never freed. So we have data in memory that's no longer semantically useful to the application, and it's just hanging around, just like consuming memory and causing all kinds of havoc. So let's just start the story by saying, this is typically what a process in memory looks like. So you have text area, data area, shared memory, stack, place for systems, heap, so, and then we have this thing called, I'll just call it C heap. And this is really known as unmanaged memory. Well, we have managed memory, so we had to have a term for this other part. So we just call it native heap or unmanaged memory. Then when you get that, set that minus XMX or minus MX setting, what happens is that when you start your Java application, it takes that parameter and says, I'm going to reserve that much memory as a malloc in a C heap. And we're going to create this other data structure, which we're going to call Java heap. And that's where we're going to do a lot of our work. So this is known as managed memory. And this is the part of memory that we're actually going to focus on in this particular talk. So be aware that we can leak just about everywhere in the gray area. But we're really going to only focus on parts of the green area here. So managed leaks is commonly known as memory leak. And so as I said, data is semantically not useful, and it remains live, so it can never be recovered, right? Symptoms, occupancy of heap grows over time, and that affects the thing that tries to clean it up, which we commonly call a garbage collector. And when we get into this condition where all of heap is consumed, then basically we try to do an allocation in that space. We get this fatal out of memory error being thrown, our JVM terminates, and that can sometimes have detrimental effects on the performance of your application. Right, on rare occasions, we actually do get this thing called an out-of-memory error happening in a single thread, and the JVM will survive. And it's okay, that's kind of weird. What's going on there? So what happens is that you'll try to allocate, and you get the allocation failure. The garbage collector will run, and then we'll retry the allocation, and we'll do it again, and then the garbage collector will run again, and then we'll try again, and if you fail at that point, then what happens is the thread dies, the allocation pressure goes off of the heap, and all of a sudden maybe there's enough room in the heap for all of the other threads to survive and continue working and stuff like that. We've actually used that as a diagnostic in finding, strangely enough, concurrency bugs in the JVM. So you can get to some weird places when this happens. Common fallacies. Running the garbage collector several times will just free the amount of memory that we need. And we're going to dive into that very deeply to see why that's not true. Yeah, failure to free memory is often blamed on the garbage collector. It's not working for some reason. And you can configure the garbage collector to solve the problem. Well, you sort of can. There is a trick to do it. The traders often do this, so they don't want garbage collection to run during the day. So what they do is they say, okay, I'm going to allocate, 40 terabytes of data today, so I'm just going to make my heap 40 terabytes in size. And, and just basically let it leak until we shut it down at night. So larger heaps in that case will solve the problem, but, generally, if you're running 24/7, that's not what you want to do. So I have this overly simplified view of heap. In the longer version, we just actually go as to how you actually build this thing. But you can see I got a piece of code here. I'm going to execute it. And I'm going to get a stack frame. And in the stack frame, I'm going to hold primitive values, of which pointers are the primitive values, as well as, there's an int in there. So that's like another primitive value. And you can see we got these, data allocated off in heap. We got this other space called metaspace, and metaspace holds the definitions, so it's like a map that says what memory actually is and what it looks like, so so that we can decode it while we're using it. So you're going to have some headers in there, and the headers are going to point to the instances, and instances are going to point to headers. So there's all this spaghetti soup going on inside here. Right. So we do tend to break the pointers down into two different classes of pointers. One we're going to call internal pointers. So with internal pointers, what we see is that the source and the dest of the pointer is within the blue square. That's going to be our Java heap space. And you can see in this case we have a number of different internal pointers in here. We also, if you couldn't guess from internal pointers, we have this term called external pointers. And as you can see, the difference here really is that where's the source? In this case, the source is outside of the memory pool that we want to collect, right? So when we actually go into a garbage collection cycle, the first thing we want to do is we want to find all of the things that are live by definition. So live by definition is anything that's outside of the memory space that's pointing into the memory space. So the first thing we have to do is we have to find these things, and that's known as a scan for roots, as you're probably already aware. So what I'm going to do is I'm going to go to all these different memory spaces, like stack frames, metaspace, code cache, other memory pools, and the list goes on of places where we're going to look, and we're just going to scan these things, and we're going to build this root set. So you can see what we're essentially doing is we're finding all of the external pointers. And I'm just going to put them into a set, and then I'm going to start working through this algorithm, which we called mark sweep, which means start from the roots, trace down. Anything that is reachable by a pointer value, like everything in this picture, is going to be considered live, right? And then we're going to sweep either in place or evacuation. We're going to use some technique to basically, at the end of the day, clean up and return memory to your application. So that gives us a nice expression. As application developers, you have an infinite amount of memory, right? Because that's what the view the garbage collector gives you. And you can just allocate, and then the garbage collector is like your mom. She just keeps coming cleaning up after you. There you go. Oh, I have some moms in the room that are saying no. Okay. So some of the things we like to do is we like to monitor Java heaps. So we want to answer some fundamental questions, right? Is the heap stable over time? And is it large enough to cope with the amount of live data that we actually have? And the other thing we actually want to look at is the allocation rate. I did a talk yesterday where I talked about the effects of allocation rates on performance. So if you're there, you'll know all about that. So The problem with the memory leak is that we're just going to inflate the live data set size, and the cost of the garbage collection is basically a function of the live data set size in modern collectors, meaning that what we're going to see is we're going to see increased GC overheads as we go on. So I think I got a chart here later on that actually shows this. So there are some tools that we can actually use. The one we recommend is going to be just turn on GC logging, collect the GC logs. We have some wonderful tools that we used to be able to give you. And we're in the process of hopefully being able to give them to you again to help you analyze these things. Yeah, sort of a part of the onboarding of RIP into Microsoft. They are now deciding what to actually do with it. So hopefully, yeah, that's a process onto its own. That's another talk. Anyways, so we prefer to use the GC logging because it's basically an event-driven journal of everything that's happened, and we can do all kinds of wonderful analysis on it to figure out what's going on. Right, and barring that, then you can just basically use things like JVM stat in the form of JCommand or JConsole or something like that to monitor what's going on. A lot of the monitoring tools automatically hook into the stuff, so they'll give you some basic information as to what's going on. So here is a heap occupancy after collection. First question, is the heap stable? I'm going to draw a straight line across the bottom there, lift it up, and say, okay, does that actually work? In terms of, does that look flat? And the answer is, yep, so far, so good, right? We can't prove what we can't see, so, but, so far everything looks okay, right? Is the heap large enough? Well, yeah, looks good so far, so, that's a different type of analysis, but, it looks okay. Now, if you compare that to this one, you're going to ask, is the heap stable? So I'm going to draw my same straight line, and I'm going to say, well, it probably looks more like that. So no, we're losing about 1 gigabyte per day. And more importantly, if you pop out into that region there, it's like, look what happened to the collections, right? As we started filling up the memory pools, all of a sudden the garbage collector has to start working harder and harder to give us this illusion of infinite amounts of memory until it finally says, yeah, give up, and pulls the curtain back, and you can see the man behind it has been lying to you. Okay. Sorry? Yes, it is. Yeah, the rebranding, I was told that I wasn't supposed to ask about rebranding for this conference, so. Or the next one, actually, which is tomorrow. Yeah, we'll just ignore that for now, right? So may destabilize applications. So it's really funny, I just did in June a large application that was destabilized. It's like, don't do this anywhere. The vendor recommendation was that you run system GCs every 2 minutes. Yeah, the results were not good. But it was very easy engagement for me. I looked really smart. All I had to do is set a flag. Don't do that. So in managed systems, memory seems to be leaking. So this is the sort of thing, right, that we looked at before, or maybe we didn't. It's in the other one's in the longer one. Sorry. I guess the thing is we're using a tracing collector. So Java's garbage collection is tracing based and it's precise. It's not reference counting like you'd see in some other runtimes. Should I mention Python or something like that, where it's not a precise collector, or Go, where they have to do other things to make it sort of precise. But the point is, it's precise. So anything that's not referenced, it's going to be collected. It's found and collected. So the unused data is. So that means the unused data is referenced in either directly or indirectly from GC root, which means that's a bug in our application code, right? So what we want to do is we want to find that bug in our application code and fix the code, and hopefully the whole problem goes away. That's the whole point of it, right? So we get into this, let's find the data that's being referenced but is no longer needed. Right, so typical causes. So this is a friend of mine said, oh, when I was writing the workshop the first time, he said, you need to put in all the typical causes. And I said, Typical causes, I think I've reduced the problem. It's really not that hard, right? So, and I said, okay, well, let's just list some of them. But at the end of the day, this is a condition you have. There exists at least one pointer chain from a GC route to a target to your target. That's what we're looking for. Okay? So, how can we find these things? Whoops, probably should have got rid of this slide. Really what we want to do is we want to get some tooling that's going to give us visibility into what our heap actually looks like. So I'm going to give you this definition, and we're going to use this to see if we can help us compose a diagnostic process. So we have object age. It's the number of collections that an object has survived. Generation, all objects of the same age. Okay, generational count, the number of different generations that we have for a given class. Okay, pretty simple. Let's put that into practice. Here's some shapes. I'll call it a shape. You tell me the generational count, right? So I'll start with cloud, since we're at a cloud event, aren't we? Okay, cloud. I got a flight to catch, so shout. Okay, 2, perfect. Triangles. Okay, half. I'll say half circle. Normally I call it half ellipse, but I don't know. I spent a lot of time in non-English speaking countries that don't know what an ellipse is. 1, yes, that's a tricky one. A lot of people say 4. So we have, it's in age 4, or of age 4, but there's only one of them, okay? And we can go, did I do triangles, stars? 4, yeah, okay. Across, it was like 2. Anyways, we can go through the whole thing. I circle 1, normal, cross, 4, cached, normal, normal, leak. Isn't that awesome? That's a precise definition of a memory leak. Okay, and not only that, you get over these weird things where people like, yeah, I had a nice long conversation. Actually, it's really funny. I actually spend more time, more billable hours talking to people and convincing them of certain things than I actually do doing real work. Like the last one I did, we spent 15 minutes diagnosing and turning off the full GC, 2 days of discussions convincing them that they needed to do this for all of their systems, right? So, and then you just run into all these weird things. So we had another one, it was like this caching, we got this caching product from a company, and they said, yeah, they didn't have any eviction policy, right? We looked at it, it says, oh, your cache is leaking. I said, what's your eviction policy look like? I said, oh, we don't have one. It's like going, excellent. You just bought yourself a memory leak, right? And you go to the company, they're going like, well, no, that's not a memory leak. That's how our cache works. And you're like, okay. Let's go back to fundamentals here. Anyway, so you can see where it all goes. Anyway, so I usually get 2 questions here to say, okay, the first is the obviousness of why is it a leak? Well, I'm creating more of these, I'm holding on to them, and if I just keep this particular behavior up, then I'm going to fill a heap with stars, and I'm going to run out of memory because I'm just going to have stars, right? So the analogy here is we're generally looking for the elephant in the room, or the stars in the heap, or whatever you want to call it. And the other one question I get, if I had a longer talk, I'd let you try to guess what it is, but why is that cached? And the thing is, like, think of your caching patterns, right? There's generally like 2 ways we cache. One is we put stuff in heap at the beginning and we just leave it there. Yeah, class loaders might be an example, right? The other one is that we put stuff into a cache and then we evict it, right? So the put into cache evict looks like a normal object lifecycle, just longer, right? Put in the beginning and use forever looks like the half ellipsed, right? So that might be a leak. We might not be using that anymore, but if it's only 1 or 2, I don't really care. It's not worth my time to find them. I want to find the stars because that's the one that's going to take us down. But you can see that the definition actually gives some distinction between caches and leaks. which is why I'm very convinced that the star is a leak and not just some funky caching going on. Okay. Right, so that pretty much covers everything here. So what we actually want to do, and we'll do this at the end, hopefully if we have time, is we want a tool that will actually give us generational counts. And JFluid, which is the, profiler within the Netbeans profiler, and you can take it out and use it in other places, actually gives you, the memory profiler will give you a generational count. And what you'll find is that if I look at the generational counts and sort by generational counts, the leaks will tend to have a generational count that's equal to the number of garbage collection cycles that you've had running, which makes it really nice and fun. Now, it's Netbeans, I think, you'll find it in Git to start. And yeah, I hope to show you at the end. I don't have a clock up because I didn't do the mirroring right. 21. Yeah, we'll have time. Okay. Yeah, memory leaks, old. Okay, so yeah, so we basically covered that. So I'm not going to go there, right? So memory leak triage, right? Recipe. Call these recipes at this point. Profile for generational counts. Make sure you have allocation sites profiling turned on when you do this. Then when you're confident you figured out what's leaking, you trigger a heap dump. And then once you've collected all this data, then all you do is you just target the object that, that's leaking, and you say, what's the causal execution path to that allocation site? And then now it's just a standard debug the logic, figure out what's going on, what the life cycle is, and what you need to do to unhook it so that you get rid of the leak, right? So it's all pretty simple. You should be able to do it in a few minutes. Now, let's talk about what leaks typically look like, right? So I always liken this to like a gang, right? It's like the bad gang in the neighborhood. And there's always like the ringleader, the thing that actually is responsible for everything coming together. And it's got all these supporting actors. And generally what you find is like, so it's like leaking field. Those are typically going to be like string, and probably for variety, string. So if you're looking for strings, where are you going to find them? Yeah, exactly. Don't look for, as I say, JDK classes don't leak, generally. I did get caught once where I had one leaking and at an inconvenient time. But anyways, generally they don't. Point is that I want to look for the leaking object, which is more than likely going to be a domain object. It's going to be the quickest, most efficient path into figuring out what's going on, right? Because my domain objects are going to have very minimal causal execution paths. And generally, there's only going to be one involved. There's going to be one place in the code where I'm going to figure out what's going on. And I'm probably going to have to make one small change in the code in order to fix it. I would say in one case, I asked the client for one method from one class, got the source code, modified it, sent it back to him, and said, here, try this. And that's all it really took, like done. Like I said, I spend more time convincing than I do actually doing real work. Okay, so yeah, focus there, right? That's the guy you want to look for, or the object or whatever. Sorry? Yeah, it's like, you need collections. They're going to be involved, so you look at structures, collections there. And the leaking object is going to have fields, so those are going to come running along. Those are going to be likely be strings. Yeah, exactly. Cool. Object profiling headaches. What a surprise. Memory profiling can be expensive, actually. Just say is. Expensive, sometimes not suitable for production environments, and may even be difficult to use in test environments. So you're going to take quite a hit. Unless you use some really interesting techniques that most profilers don't use. Memory profiling distorts the allocators. Not quite true for flight recorder, but then the quality of information you get from flight recorder isn't what you get from other profilers just because of how it actually works. Right, so we get if you saw my demo yesterday, when I found the hot allocation site, it turns out that it wasn't really a problem because the optimizers optimized it away. So if you basically change the code there, then, you know, yeah, so there's some problems there. So generally, we don't have to worry too much about it when we're doing memory leaks, but you do have to worry about it when you're doing other type of memory profiling. So the alternative technique is to just take a snapshot of the heap, right? But this is a single point in time. Like, we have a problem of dynamics. Something is growing. We want to watch the growth, right? If we get a single snapshot, it's only what it looks like then, which can make it a little more difficult to do the analysis. But we do have a technique we can use, and this is called using Dominator trees, right? So if you look at this particular graph here, you can see I got some green, red, black, gray things. Like, so you consider this to be an object graph, right? The dominating object in this graph is going to be the red one. You know, it seems to be at the center of attention in this case, right? So it's any object in an object graph that must be passed through to reach any other object. And in this case, we get this as being a pinch point. So what I'm going to do is I'm going to calculate retained set size. So basically, I want to know the size of the set of black things. That's an immediate dominator. And, you know, there's a dominator tree. The gray object may or may not be included. It depends on the tooling's interpretation of dominator. But it's part of the retained set size, but it's not strictly reachable by a single object. So it's kind of cool, because if we get a heap dump, what we can do is just run a query over the heap dump that says, find these things. Okay, so guess what the number one top hit is going to be? Caches, right? That's exactly what a cache looks like. So you can tend to get a lot of false positives, whereas when we're using generational counts, I don't need to know anything about the domain, like nothing. I don't really need to look at source code. Nothing. It's like, give me the app, let me run it, and we'll sort it out. In this case here, you really have to go sorting through things and figure out, okay, what's happening here? And then you also have the problem that maybe it is the cache that is leaking for bad eviction policy and stuff like that. So it's a little trickier, but it's still very effective, and you can still find things. So here, acquire a heap dump. You can do it when you get out of memory errors. I'd suggest not waiting that long. The current set of tools that we have don't really scale well to larger heaps. So I have been very slowly working on a tool that hopefully scales. I call it JHeapo, which you can get at the Adopt project. And help me build it if you're interested. So we're using Neo4j as the backend. Gives me something that should scale. And it should give me GQL as a standard query language for getting information out. So after we get the heap dump, we're going to calculate the dominator trees, and then we're going to start looking for the elephant. In other words, who has the largest retained set size. How are we doing? Oh, 28. Oh, we're going to have lots of time here. That's excellent. Right. Okay, cool. So we have about 15 minutes for a demo. I'll take questions now also, or at any time, just shout them out. Yes, sir.
I heard there's a new garbage collector, no-op one.
Epsilon. Yeah, isn't that fun?
Like helpful option.
Well, I've never thought of it actually being helpful to. Okay, so for those who don't know what Epsilon is actually a no garbage collection option. So there's no garbage collector in the JVM at all, which is really kind of fun, because really what you're saying is like, I don't want to take the throughput hit of having to go through all the read barriers and things like read-write barriers and everything when I do stuff like mutate or move or just plain access. And so if I don't have a garbage collector, I don't have to cooperate with the garbage collector, so I can take all that barrier load off, right? So if you look at ZGC, wrong country, ZGC. If I look at ZGC, then the barrier hit is approximately 15% on your throughput, right? You look at Shenandoah, the barrier hit is approximately 15%. G1, it's approximately 10%. If you do a comparison to like a parallel collector, right? And CMS, there's something like probably about a 5% hit or something like that. But if you go to epsilon, then your hit on throughput is like 0. It's really nice. Right, well, compared to the parallel collector, it's even faster then. So I guess it's like a negative if you use parallel as our baseline. No, because you'd still be creating temporary objects that would be normally garbage collected out. So yeah, it's an interesting thought. But yeah, since you are creating temps and there's no garbage collection running, the temps are just going to consume memory, and that's going to be it. I like that idea. That could be like a nice trick question, right? Yeah, so if you're not allocating at all, then I would say that's a good technique. If you think like, oh, I'm doing 0 allocations, which some applications actually do. We've worked on a number of applications that have 0 allocation rates. You do some initial setup and stuff, and then bang, you're done. Those go really fast. Oops, almost did it again. Almost pulled the sound off. Okay, so I have this wonderful application here, which I call Leaky. I'll let you guess what it does. And if I just run it, you can see that basically, so what I've done here is, let's look at some of the source code, why not? Oh, right, I'm giving away the goods here. I'm showing all the class names. Okay, doesn't matter. So let's try Leaky. So basically what you can see here is like, is that better? You can see that now, right? So I'm going to do stuff, and that's my heap occupancy afterwards. All right, so how am I monitoring that? Then we can actually just look at that and say, let's get rid of that. We don't need that. So there is some, part of the serviceability architecture, it does have some internal performance counters that you can actually look at to get some stats out of the JVM. And in this case here, right, you can see what I'm doing is from the manufacturer, I'm getting the memory MX beans, and from the memory MX beans, I'm actually getting, maybe it's easier to read this way. Yeah, okay, yeah. I'm getting, the occupancy, how much memory is actually in use and stuff like that. And so we can just pop that up into our application. So every time we do stuff, it's like, yeah, our heap occupancy goes up. And when we get this balloon thing happening, or the beach ball, then it's probably a garbage collection cycle running and everything like that. Okay, so the question is like, how can we use some of the tooling to figure out, why this thing is leaking, and actually which class is leaking if you can't figure that out by the names. So I will switch to Visual VM here. I thought of doing Flight Recorder also, but maybe 33? Yeah, if we get ambitious. So I'm going to do a Visual VM. Are we still running? No, we need to be running, right? No, we are running. Are we running? Yeah, okay. So there's Leaky. There's Leaky. Okay, so now we are attached to Leaky. Here, and let me just have some fun with this. There, and yeah, okay. So we can actually see what's going on a bit. It's all right. So there's our profiler, our JFluid profiler. I'm going to go to the memory settings, and really what you want to do is any profiler you use, make sure you check the filters and know how it works, because the one thing you don't want to do is filter the bottleneck out of your profile, right? And end up tricking yourself. So in this case here, I'm just going to look for everything because I don't know what I'm looking for. So I'm just going to look for all classes, all arrays, attach the memory profiler, get rid of the settings, and boom, there we are. Look at that, generations right over there. So I can just sort of sort this whole thing by generations. Let's see if I move this over just a little bit. Okay, and wow, we have floats in there. Okay, that's fine. But you can see everything's about generation 1. That's quite normal. You can see that the vast majority of the classes are going to be have a generational count of 1. So let's do stuff. And, oh, wow. Okay.
So, sorry, by generation, do you mean like a snapshot in time?
Generation? No, this is actually the generational count as I defined it. Like, how many different generations of Java-Lang object array are there? Okay. How many different generations of car array are there? How many different generations of the, whatever the next one is, array, dollar array, hash map entry, I might guess, or something like that? No, this is actually part of the tool. This is what JFluent does. It actually will calculate the generational count. I mean, you could do this yourself. It requires a little trick with getting garbage collection counters and playing with phantom references and fun things like that, if you're interested in building your own. But yeah, that's pretty much what it does. So anyways, where are we? Do stuff again. And really what we're seeing is that we're going to end up with, just to make this a bit smaller, sorry for the back. What you can see is that we sort of just like have this cliff effect here, right? You see that? It goes like 11, 11, 6, 1, 12, 5. And really what we're seeing is that, okay, these are all of the things. Remember, so this is the gang, right? So where's the thing that we're interested in the gang? Sorry, I have to just make it a bit bigger to make it a little bit more usable. There's something funky going on here, right? And yeah, so like where are the domain classes? Well, you know, there's leaking class, leaking field, right? So pretty much in this application, we've identified that leaking class is leaking and probably some association with leaking field. We can get the allocation stack traces right here, which is really nice. Yeah, does that make sense? So that's how I'm actually, you know, that's the allocation site right there, called the constructor, the allocation site for the object array, which is also leaking. Yeah, so you know, so let's go on to the next step, and let's see if we can actually take a heap dump, and this should load up into the heap dump. Creating heap dump. Wow, that's coming along very quickly. Yeah, sometimes getting the tools to cooperate can be challenging. Yeah, getting customers to cooperate, challenging. Tools, even more challenging, right? I mean, who has that experience? Actually, I should ask who are customers first, so I know who I'm insulting here first. Okay. Okay. So we can just look at this like, okay, what are the objects? Now we can just go through, and we know what we're looking for. It's that one there. And so now here's all the instances of it, so we can actually see what they look like. Here's our fields. What a surprise. Leaking field is part of leaking class. And we have these other things that are actually in there just to make things more massive. So you can see pretty much it's really mechanical at this point in time. As to what's going on. So, you know, there's other things that we can actually do here in terms of figuring out, oops, sorry. There's like a bit of annoyance with that one here. Yeah, anyways, you get the idea. So we have enough information here. We can start looking at dominators. We can do a dominator calculation right here. We can find the GC roots, which is like kind of nice. This can sometimes take a bit. Hopefully this heap is not big enough. Okay. That we can actually, where did it go to? Oh, right. Well, these are GC roots, but we should be able to calculate here paths to GC roots. Right. So that's leaking class. Oh, so this instances again, but it's fields references. Sorry, here it is, right here. My bad. So now it's on a path where it's computing. What are the things that are referencing me? So I can see the data structures that it's contained to, and I can trace this all the way back to a GC root, so that you really have a deep understanding of what's going on by the time you go back into the application. So if we go back to the profiler here, while it's calculating that, we can see there's our leaky model. So if we go back into the source code, I'll make this as big as I possibly can. You can see that leaky model is right here. So I mean, this is just kind of like a silly thing. So I'm just collecting these strings onto an array list and stuff like that, so rather contrived. When you do it in bigger applications, sometimes it does take a little time to sort of to wiggle through the logic, but you know, eventually you'll get there. All right, so here it is. So there's a little bit of a guide there to tell you what it is to help you understand what you're looking at. Oh, sorry, that's the wrong one. Oh, right. Excuse me. Over here. Yeah. So, anyways, at this point in time, we can just follow the words. So that's weak reference. Okay. So that's profiler artifacts. So you do have to be careful of that. But you can see there's our leaker. There's our model, right? And then we're in some sort of like hash map thing here. And anyways, we can trace this all the way back to the GC root, and we get a good understanding of the anatomy of what our heap looks like, and you know, probably have a really good understanding of what we need to do to fix this particular application. Okay, and that says 5 minutes, so I'm really happy to take questions now for the session. Anyone has them? Yeah, this is Visual VM. You can get similar types of information using other profilers. I'm just using this one here because, not for any particular reason. So, well, Visual VM is the only one. JFluid and Visual VM is the only profiler that actually gives you the generational counts. None of the others will. Some advertise, but they're lying to you. They try to give you an equivalent, but they don't actually will give you this level of detail. So you have to do snapshotting and stuff like that to figure out what's going on. Yes?
Have you found any particular domain or style of application that might perform better than others?
Oh, yeah.
Versus batch processing versus some long-lived, is there like an area that can perform?
Oh, yeah. If you like statics, you will leak, right? If you like giving like free-wielding access to all of the variables inside your data and stuff like that, you know, like the getters are evil type thing, you will leak. There's just this open style of program where there's like little encapsulation and what I call little encapsulation of state, behavior, representation, all that stuff. We tend to find far more performance issues in that style of application than we do in anything that's written where, well, you know, I would just say that, you know, the rule of thumb has always been, you know, control state, internal state, and minimize the visibility of every variable in your application, right? So fields are preferred. If you can't use a field, then of course, yeah, then we'll accept, local variables are preferred. If you can't use the local variable, then yeah, we're okay with fields. By the time you go to static, if it's not final constant, then you know, forget it. You've lost me at that point. Yeah, so that's it. I think the other thing is like collections of collections. As soon as you start doing that, you're missing abstractions in your model. And that's just a sign that you just have bad modeling, and that tends to lead to leaks also. Because then, you know, it's just easy when you get collections of collections of collections, just to forget to unhook something, and all of a sudden you're just basically, you know, boom, right? So there's those types of things that we find. So better modeling leads to better performance. Localized variables leads to better performance. You get better optimizations from the compiler. There's less visibility, so the compilers are able to do more. It's just, you know, it's just an across-the-board win. Easier to reason, fewer logic errors, you know. So it's not just a performance issue. Okay. Yes? Oh, right. So there's just a number of flags you can use to turn it on. So I have a whole talk on unified logging. You can probably look it up on SpeakerDeck or SlideShare. I think I've launched them both up there. In Sensum, I'll just start it up here. And you can see how do I create a GC log file? And you see, basically, these are the settings that we actually recommend for unified logging. So it looks something like that. For JDK 8, then you end up using these things here.